Welcome back. So what I want to do here is define the identity permutation. The identity permutation in the symmetric group of permutations of S for a set S is the function that fixes every element of S. The identity permutation in Sn is denoted by epsilon, and it is the permutation where each element is being fixed. So one goes to 1, 2 goes to 2, dot dot dot, n goes to n. So epsilon applied to x is equal to x. So that's the identity permutation in Sn. If we have a single cycle in Sn, then the order of the cycle is equal to the length of the cycle. So for example, if I have the cycle 1, 2, 3, if I square that would mean that I am multiplying 1, 2, 3 and 1, 2, 3. Now multiplication means composition here. So when we take the composition of these two, we get 1, 3 and 2. And let's check that 1 goes to 3 here. So if I want to know what this product does to 1, we apply this cycle to 1. So this one takes 1 to 2 and this one takes 2 to 3. So then we see that 1 goes to 3, and then you can check that 3 goes to 2. So notice what's happening when I am squaring 1 to 3. Basically what happened is that 1 is skipping and going, so we are skipping one space here, so 1 goes to 3, and then 3 goes to 2, and 2 goes to 1. So, and if I take if I take 1, 2, 3 to the power 3, so that's multiplying 1, 2, 3 3 times, which would be the same as multiplying this with 1, 2, 3. So multiplying this two, and you can check that if you do that, you get that 1 goes to 1, 2 goes to 2, and 3 goes to 3. So you get the identity permutation. So the order of 1, 2, 3 is equal to 3. Now how about 1, 2, 3, 4? If I take the cycle 1, 2, 3, 4, and if I square that, so this is what I'm getting. And so notice that when I multiply, then I'm going to get that 1 goes to 3. So I'm skipping one element here. So 1 goes to 3, 2 goes to 4. Okay, 1 goes to 3, 3 is going to go to 1, 2 is going to go to 4, 4 is going to go to 2. And when I take the cube third power of 1, 2, 3, 4, so that would mean that I have to multiply this with 1, 2, 3, 4. Now this time what's going to happen is that we're going to skip 2 elements. So 1 is going to go to 4, 4 is going to go to 3, 3 is going to go to 2, and 2 is going to go to 1. And so we get 1, 4, 3, 2. And when we take the fourth power of that, we are just going to get that 1 goes to. So now we're going to skip 3 places here. So 1 is going to skip 3 places, so it's going to come back to 1. 2 is going to skip 3 places, it's going to come back to 2. So this is going to give us the identity. So the order of the cycle 1, 2, 3, 4 is 4. So you can see that the order of a cycle is equal to the length of the cycle. So if I have a single cycle, then you can see that when I square that, when I square a cycle, what happens is that each element is assigned to the so basically 1 goes to 3 by skipping 2 here, and then 2 goes to, so 1 goes to 3, and then 3 skips 4, and then it goes back to 1, and so on. The order of an element alpha written as a product of disjoint cycles So remember that any permutation alpha can be written as a product of disjoint cycles, and the order of alpha is the least common multiple, or LCM, of the lengths of the cycles. LCM of the lengths of the cycles in the product representation of alpha. So the order of, for example, what's the order of the permutation here, where we have alpha, a product of disjoint cycles here. Now the first cycle has length 4, next one is 2, and the next one has length 2. So the LCM here is 4. So the order of alpha will be 4. In S7, there are 7 factorial elements. So 7 factorial is equal to 5,040. So S7 has 5,040 elements. We want to determine the orders, we want to determine the possible orders of the elements of S7. We only need to look at, do we have to find the order of each of these 5,040 elements? The answer is no. So we can look at the possible cycle structures of the elements of S7 and find out the possible orders of the elements. So notice that every element of S7 can be written as a product of disjoint cycles. So as products of disjoint cycles, how many ways can we express the permutations in S7? So maybe we have a cycle of length 7. So then all these symbols are covered here. Or maybe we have a cycle of length 6 and a cycle of length 1, in which case the order of the element would be 6. We might have a cycle of length 5 and a cycle of length 2, and in which case the order would be 10, because that's the LCM of the lengths. But we also may have a cycle of length 5 with a cycle of length 1 and a cycle of length 1. In this case, the LCM is 5, so that's going to be the order of such an element. Let's now look at the cycle structure where the largest cycle length is 4. So if we have a cycle of length 4, then we may have a cycle of length 3. So the LCM would be 12, so that's the order. But if we have a cycle of length 4, then we may have a cycle of length 2 and a cycle of length 1, in which case the LCM would be 4. We also may have a cycle of length 4 with three cycles of length 1 here. In this case, the LCM would be 4. Now, so these are the only possibilities with the length 4 being the largest length. Now let's look at cycle structures where length 3 is the largest length. So if we may have a cycle of length 3 with a cycle of length 3 with a cycle of length 1. The LCM would be 3. We may have a cycle of length 3 with a cycle of length 2 and another cycle of length 2, in which case the LCM would be 6. And you can see the other possibilities here, which I will let you look at. So you see, there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. There are only 15 possible disjoint cycle structures in S7, and then we can see the order for each of those cycle structures. Okay, so now we know that in S7 we have elements of order 1, 2, 3, 4, 5, 6, 7, 10, and 12. Okay, so now let's say that I want to know the number of elements of S7 of order 3. Well, if we have an element of order 3, then how will the disjoint cycle structure of that element look like? So if alpha has order 3, then the cycle structure of alpha as a product of disjoint cycles can only contain cycles of length 1 and 3. So either if alpha has order 3, then the disjoint cycle structure of alpha will either be a cycle of length 3 with a cycle of length 3 and a cycle of length 1, or it could be a cycle of length 3 with 4 cycles of length 1. Now we don't have to worry about the cycles of length 1, we can delete them. Now the question is, we want to know how many elements of S7 have order 3. Well, so we need to count how many elements in S7 can have this cycle structure. Well, notice that if we are creating a alpha with this cycle structure, for the first space here we have 7 choices, and then we have 6 choices for this one, and then we have 5 choices here. Now remember, these are disjoint cycles, so if I have 5 choices here, then for the next cycle I have 4, 3, and 2 choices here. So we see that we have 7, 6, 5, 4, 3, 2. Those are the choices for each of these places, and so if we multiply them, that's how many. So this numerator here is how many ways we can rearrange the elements of 7 here. Sorry, how many ways can we rearrange the elements 1 up to 7? But remember that if I have a cycle, the same cycle can be written in. If I have a cycle of length 3, then we can write that cycle in 3 different ways. So therefore we are triple counting those cycles. So then I have to divide by 3 because we are triple counting here. We're also triple counting here. So I have to divide by 3. Now I also need to divide by 2 because notice that if we change the order of the 2 cycles, it doesn't change the product. So because disjoint cycles commute, so it shouldn't matter if we order is not important here. So but the numerator is actually double counting. So we have to divide by 2 as well. So that's how many elements we have with this cycle structure, and you can figure out how many elements we have with this cycle structure here. This is actually easier than the first one, and then we add up those numbers to see how many elements of order 3 we have in S7. Okay, so let me stop here, and in the next video we will finish off our discussion on permutations.